Okay, this lesson is going to be on interval notation. For Algebra 2, this is going to be less than 15. For Algebra 1.5, it's going to be more like 22 or so. Once I know for sure, I will make sure I describe it correctly on the YouTube upload. This lesson is about learning to write and read something that you probably do not already know how to write and read in mathematics. And it's called intervals, or interval notation. Notation is always a signal that, hey, you're going to learn what something means in terms of being able to read and write it. And so it's going to be with inequalities and number line graphs. Okay, so what is an interval? An interval is a subset of the real number line, or it's a part of the real number line. And generally, it's two endpoints, say 6 and 8, and all the numbers in between. And you may or may not be actually including the endpoints. Like in this case, the endpoints are open. Okay? And so you've already done inequalities. You've already done graphing on a number line. The only piece you have not done is these intervals. And so you have here the interval 6, 8 includes any real number between the endpoint 6 and 8, but not including the 6 or 8 because these are open. If these were equal to's, these would be closed. These would be closed. So if we change this symbol to or equal to, we change this to closed. Well, that means we should also change the parenthesis. And so it turns out you're going to use brackets as the other symbol. Okay, let me actually pause there. I don't want to go any further forward until we've sort of looked at this. So here we go. Just using arbitrary endpoints A and B. This interval is the same as, actually let me change colors here. So it's the same as this inequality. Okay, and it's the same as this graph. Open endpoints. Not a very good graph, but it'll work. Whereas if we change the parentheses to brackets, we're dealing with or equal to's, which means that in the graph we would have closed endpoints. In fact, I've seen books where instead of using the open and closed endpoints, they actually use parentheses and brackets. I don't particularly care for that, but it's out there, so I thought I would mention it. I wanted to point out, if you're having trouble trying to keep these straight, the best mnemonic I have, the best way that I have to help remember it, is that if you take your hands and make a circle and then break it apart, it's the parentheses on the interval, which works pretty well. And then the top and bottom part of a bracket is a really spread out equal sign. It's too horizontal. And so it's not great, but it's the best I've got. So if you've got these two, then predict this, and hopefully you could actually now at this point maybe even fill in most of this yourself. Oh, this is a parenthesis. Parenthesis was less than up there. Ooh, this was a bracket. Oh, the bracket right here was less than or equal to. So it's A is less than X, and X is less than or equal to B. So it's open at A, but it is closed at B. And it's possibly any number between A and B, including the B, but not the A. Well, what's it mean if it's bracket A, comma, B, parenthesis? Well, that's just sort of the reverse version of the one above it. A is a closed endpoint. B is an open endpoint, and you connect those. What about these? Well, same basic idea, except we've thrown in some infinities, and we can't ever actually include infinity, so there won't be a second endpoint like down at the end of the number line or anything like that. And so actually on these I'm going to start with the graph, because at least on this first one, because it might help you understand the inequality a little better. So here's A, which we don't even really care about. Here's B, and we're looking at an open endpoint at B. Okay, sorry about here I am back. So we were looking at this interval, and it's got one definite endpoint at B, and then it goes all the way down to negative infinity. So it just goes whoop. And so as soon as you look at that graph, you probably realize, well, oh, that's just x is less than b. It does not have a left-hand endpoint. So what would this one be? Well, this would be x is less than or equal to b. So we would draw a quick sketch. There's A, there's B. We've got a right-hand endpoint that's closed, and it just extends indefinitely to the left. Well, okay, I guess this would be x is greater than A. So there's A, there's B. This is open at A and points to the right. Whereas this is x is greater than or equal to A. So there's A, there's B. We are closed at A and pointing to the right, which kind of leaves only the last row of the table as a mystery. Hope I mentioned that we were filling out that table. If I didn't, I apologize. What in the world does this last one look like? Well, this last one, let's change the ink for just a second. It's a little different than the rest. I mean, I didn't write any of the infinities up here, but here I guess I'm going to, just to kind of make a point. All this is really saying is that x is a number between negative infinity and positive infinity, which really isn't all that helpful. All you're really basically saying is that x is a real number at that point. So what in the world does this then look like? Well, basically, it's the entire number line would need to be shaded at this point. Okay, sorry, more interruptions. So the point is, though, this would be the entire number line, the entire real number line. Okay, so a little bit more just about intervals, kind of specific. Geometry, specifically length or measure. You just subtract the endpoints and take the absolute value. How far apart are 6 and 8? 2. So it makes sense that the length or measure of that interval is 2. What's the midpoint of 6 and 8? 7. But you're hopefully not terribly shocked with that midpoint or center of that interval is you take the endpoints and you average them. You add them together and divide by 2. 6 plus 8 would make 14. 14 divided by 2 is 7. So, and then the point is that the stuff that you kind of already know, it just might look a little different, works no matter what kind of interval it is. Realize that for these intervals where an infinity is involved, You don't really talk about the length or measure or center of these. That's more for the ones where there are definitely two endpoints. So a little bit more about that is the idea of bounded. This example is totally or completely bounded. I mean, it's got a boundary over here, it's got a boundary over here. Whereas this interval is only bounded on the left-hand side or for the lower numbers, so it's bounded below. This interval is bounded above or to the right because there is a limit that you cannot cross, so to speak. And so you go back to these intervals were all totally, completely bounded, so they have a definite length and a center. Another word we might use here is I meant to grab red. Besides bounded, or we might also use the word finite. Ooh, what is the pen doing? We might also use the word finite here. Whereas these intervals are not totally completely bounded. They're going off towards infinity in one direction or the other, or in the case of this one, both. And so these are infinite intervals. Alright. Before we do this, actually, got an example to do real quick. Sorry about that. So we want to write this as an interval. And if the directions are just write this as an interval, you don't have to do this step, but for some of you that haven't done anything like this before, it might be helpful. So they're like, well, at least to get started, I know the graph. I know that's the graph. So what's the interval? Well, that's open, so that's a parenthesis at 0. Pen's having trouble all of a sudden. And then the other endpoint's 10, and it's also open. So here's the interval. By the way, we'll sometimes name our intervals like capital I equals. So just in case you see that, don't get too worried about it. Again, if you needed to mentally think about this as a number line sketch, you go, well, that's open, that's closed, they're connected. So the interval is -3 in parentheses, but the 5 is closed, so we use a bracket to show that. This one, if you think about, okay, well, what would the number line graph look like? Just a quick rough sketch. Oh, it's open at 2 and just goes off to the right. Well, where's it going to? It's going towards positive infinity. So the interval here is open at 2, comma, positive infinity. And you'll never be able to include infinity because that implies that infinity is an actual number. And it's not, it's a concept. And then, so here we go -11, 1. We're open at -11 and pointing to the left. We're closed at 1. Oops, got a little red there. Closed at 1 and pointed to the right. So this one's kind of the toughie. Let's see, it's negative infinity down here, positive infinity off in this direction. This is actually two different pieces, so we need two different intervals. It's negative infinity to -11, excluding the -11. It's open. It's closed or inclusive at 1 and goes off towards positive infinity, which you can never include. And we want to think about these two pieces as being one thing, even though they're not really connected. And so we use our union symbol to connect those two pieces. Alright, and so as you can see, I mean, that's about it. It wasn't too hard, but we got these two examples left, and you can see I've got quite a bit of work there. So that's only been, a little more intense. But then now we're going to probably spend another 10 minutes just on those two problems. And the idea is that they're going to be nonlinear inequalities, and you're not going to really be able to solve them in the traditional sense. You got to use what I call, and I wouldn't be the only one to call them this, numerical techniques. And you're going to get into something called critical values and test intervals. And I don't really want to spend a lot of time talking about these because I'd rather just show you in action this problem. And so let's see. It's an inequality, so we know that there's going to be a number line involved. Okay. Well, what are the critical values? Well, the critical values for this particular problem would be if x were equal to 1 or if x were equal to -3. And probably a few of you are going, well, where'd those numbers come from? And hopefully a lot of you are going, oh, okay, I see why we were talking about earlier in the year in like the special numbers lesson and a couple other places, this idea of, this multiplication that looks like this, and we had been doing it equal to 0, now it's greater than 0, but it's the same idea. What would make this 0? Well, when x is 1. What would make this piece 0 when x is -3? So if one of these two factors is 0, that's going to be sort of your critical comparison to 0. So those are your critical values. So we go ahead and we'll come over here and we'll put those on the number line. 0, -1, -2, -3. So there's some other numbers. And then probably the easiest way to think of this is to think of those critical values are actually like cutting that number line into 3 parts. And those parts are what we said were going to be called test intervals. So the test intervals in this case are -∞ to -3. Oh, my space. -∞ to -3. And that's our first cut. And then between the cuts is -3 to 1. The actual cut gets to be part of, gets to be endpoints, and you'll see it. And then 1 to infinity, you'll see it in both the interval. Or you'll see it in 2 intervals, I guess I should say. Sounds a little better that way. Alright, and from there, okay, what happens? From there, you now need what I call champions, which is like a reference to a long, long time ago. If we were like 2 rival kings and we were at war and we were about to fight a battle, we might ride out and meet in the center of the field and talk and say, there's no reason for us to just completely slaughter each other. How about you send out your best fighter and I'll send out my best fighter, and they'll fight, and then whoever wins, we'll settle it that way. Let's not make everyone fight. And so you would have to decide whether or not you felt like that was a good strategy for you, and it occasionally happened. And so what we need then is a champion for each test interval who's going to represent this entire interval. And so a great champion over here might be 2. And a good champion in here might be 0. And a great champion over here, -4. I could have also picked 17 or -1.5 or -17,000. But you tend to pick ones that are kind of nice numbers and are, just going to be easier to work with. And then after you do that, I usually do it by sort of setting up a table. So let me show you how to set up a table. We're going to have 3 columns. An X column, the left-hand side of the problem column, and the right-hand side of the problem column. I'm going to put greater than 0 as a reminder that that was the right-hand side, and then we're going to just sort of fill this out. You'll see in a second as we get. Okay, so I'm going to go ahead and I'm going to write in my 2 critical values here were -3 and 1. And then I also selected as champions 2, 0, -4. I use the color coding to emphasize where these numbers are coming from. Realize that it should alternate. It should be like champion, critical, champion, or something kind of like that. When I do it on the board, I'll even also draw in boxes around these. So let's see if I can do that neatly. And if I can't, I'll just not do that. That's not too bad. And I do these boxes just to even further emphasize that these two are critical values, okay? That's where these two came from. And so there's your table. And let's fill out the table. Oh, I guess in this gray right here. We'll start at -4. Well, you're going to put -4 in for these x's here. So it'll be -5. -4 minus 1 is -5. Times -4 plus 3 is -1. And -5 times -1 is 5. And that is greater than 0, so I'm going to put a check mark. Okay. It's like this champion rode out to battle, and it won. Good job, -4. So, and the idea is that if -4 checks, it works. Then if you check -5 or -6 or -3.2 or -17,000, anything off of, it's like you take a piece of string and you cut it up into 3 pieces of string, and then you just inspect that one piece of string, and -4 works. So the entire piece of string, the entire interval works. Okay, so this interval gets a check. Alright, so let's check 0. I'm going to come back to these. 0 minus 1 is -1. 0 plus 3 is 3. So -1 times 3 is -3. I compare that to 0. No, it's not greater than 0. So 0, you failed us. This entire interval has been put to shame. Where is your honor and dignity, sir? Of course, not everyone can check, so I guess you can have some of your honor and dignity back. 2. We check 2. 2 minus 1 is 1. 2 plus 3 is 5. 1 times 5 is 5. 2, you are a fine champion, because when I compare this number 5 that I get from substituting 2 into this problem, it is greater than 0. So this interval, we tested it, it works. We tested this interval, it did not work. We tested this interval, it did work. We did those tests by selecting these representative values, or champions. And don't assume that it's just always going to be like works, doesn't work, works, or something like that. It's not a guarantee that it alternates. Let's check the champions real quick, see what happens here, just so you see. -3 minus 1 is -4. -3 plus 3 is 0. That's why -3 is a critical value. It gets you a 0. When you multiply, that's 0. And 0 is not greater than 0. So I'm going to put a little O here for like open endpoint. The critical values are endpoints. So that's an open endpoint. That worked. That didn't work. 1 minus 1 is 0. 1 plus 3 is 4. 0 times 4 is still 0. That's an open endpoint. So here we go. Let's go up to the picture and make it match our table and all of our work here. There are open endpoints at the critical values at the cuts of -3 and 1. This did not work, so no number in here is going to work. But the ends did work. -4 works, so this entire interval is going to be true x values for this original inequality. Same deal with 2. And so we need to write a solution, and I'm out of space, so I'll pop up Doodler here real quick. The solution is, and then also this inequality, x is less than -3, or x is greater than 1. And it's also the same as this interval. They're all open, So it's all parentheses, but then it's two distinct pieces, so we have to union it together. And I know that seems complicated, but with a little practice, and if you can remember the general process, it's not too bad. So what about this one? Alright, so let's see here. Let's, real quick, critical values. Well, x being -4 would cause the denominator to be 0, and we know that's a problem. And with a little bit of work, you can hopefully decide that if x were -1/2, that would cause the numerator to be 0, and that's also a little interesting. And so number line graph, -4 is a critical value, and then we're not worrying about scale or anything, it's just to help us stay organized. -1 is also a critical value. And those are our cuts. So our test intervals are from -infinity up to and including up to but not necessarily including -4, -4 to -1/2, and -1/2 to +infinity. So we're going to set up our table. We're going to test some, I'm boo-booed that a little bit. It's negative, and there's a fraction, and it's 2x plus 1 over x plus 4. I started to put the negative in the numerator, and you would have to distribute it and be real careful about how you're changing signs. And so I'm gonna avoid that for a second. All right, I'm gonna put the critical values here in red. -4, -1/2. And some of you are going to go, okay, well, it was less than or equal to, so I'm going to go ahead and fill in my solid circles over here. And to that I say, not so fast. Watch what happens. -4 in for x would be -8, plus 1 is -7. -4 plus 4 is 0. The negatives do cancel, but you still can't divide 7. You still can't divide 7 by 0. That's a problem. It's undefined. It would be bad to abbreviate because I'm running out of space. And so we can't compare that to 0. So this actually ends up being an open endpoint. Whereas -1/2, you get the negative. 2 times -1/2 would be -1. -1 plus 1 is 0. -1/2 plus 4 would be 3.5. Well, it doesn't matter what else is going on. That's still going to be 0, which does check. It is going to be less than or equal to 0. So this is actually a closed endpoint. So not so fast, fellas. What we got going on in this problem is an open endpoint at -4 and a closed one at -1/2. Now we'll check some champions. A number down here that's going to be somewhat decent is -5, -1 out of this middle interval, and let's go with 0 out of the other interval over here on the far right. So we've selected a number out of each of these intervals, and we check those. And let's see what happens. It'd be -10 plus 1 is -9. -5 plus 4 is -1. There's already a negative in front as well. So this ends up becoming -9, which indeed is less than or equal to 0. So this entire interval works. So I know that because -5 works, which I hadn't put in the champions up here. 0. Oops. Should have been -1. 10, that's a -1. 10, you didn't see me start to make that mistake. Anyway, this interval worked. So any number down here is going to work. Ta-da. Now we check -1. Well, 2 times -1 is -2. -2 plus 1 is -1. -1 plus 4 is 3. But wait, it had a negative in front of the whole thing. So it works out to 1/3. Oh, 1/3 compared to 0 is not less than or equal to 0. So that interval failed. So far it's kind of got the same basic structure, except I needed to show you this bit about it's possibly open on one end but closed on the other. Let's check 0. 2 times 0 plus 1 is still 1. 0 plus 4 is still 4. We had a negative in front. That's a fairly small, it's actually close to 0, so it's actually greater than most negatives, but it's kind of close to 0, but it is still negative, so it is less than or equal to 0, so it does check. This interval works. So we go back up to our graph and say, okay, here we go. There's the picture. Now that we've got the picture, we can, clear this out. Let's see here. What do we have? X is less than -4, or X is greater than or equal to -1/2. So we're interested in the interval -infinity to -4, and the bracket, I was going so fast I almost messed up. The bracket -1/2 positive infinity. We're going to union those two intervals together, and that's our solution. Please realize this is all the same information presented 3 ways. Here's the inequality. Here's the number line graph. Here's the interval. All 3 of these, if you know what you're doing, if you know the notation, say the same thing. Thank you. I'll come up with something for us to work on in class to kind of make sure you get this. Probably do a couple more of these harder problems together. I'll see you next time. See you in class. Thank you. Sorry that there were a lot of stops and starts in this video. Good luck.